Hello everyone, I'm Marcio from Federal de Santa Catarina, Brazil, and I will talk about the use of logical refactoring and approximate computing to improve power and area of Gaussian filter designs. So, my presentation is divided into three parts. The first one is an introduction, where I will present the basic concepts. Following, I will present the approximations used in Gaussian filters. And finally, I will present and discuss some experimental results and the conclusions. So, in the recent years, the adoption of IoT and mobile devices are increasing. In 2018, there were 6 billion of IoT devices, and it is forecasted to reach 50 billion of devices in 2023, which means an increase of more than 2 times in 5 years. But those devices have limitations in power resources. They normally use batteries. Also, for each new device generation launched, new features are introduced, putting more pressure on the power resources. And the combination of those two things demands new approaches to deal with power resources. One approach that can be used from programming language to transistor level design is the approximating computing. In hardware design, this approach can optimize area and power at the cost of reduction in precision of results. Due to this precision reduction, the most suitable applications to approximate computing should be error tolerant. Some examples are the DSPs and multimedia applications. So, the multimedia applications explore the limitations of human sensory system, like vision. Also, those applications are computer intensive as they demand a lot of arithmetic calculations. Many of those applications are used into real-time applications, which demands dedicated hardware. Among those multimedia applications, the border detectors are relevant because they extract features from images. Also, they are used in ubiquitous scenarios that demand energy-efficient processing. To improve the results of border detectors, it's performed a pre-processing step using filters to reduce undesirable effects like noise. The Gaussian filter is largely used in the pre-processing step of border detectors. In the case of the K-edge algorithm, Gaussian filter uses between 30 and 40% of total execution time. So to reduce this execution time, it's mandatory to use the dedicated hardware. Also, the Gaussian filter is a common application to evaluate approximating techniques. So, the goal of this work is to evaluate the three different approaches and its combinations to optimizing power efficiency of Gaussian filters. The first one is the logical refactoring to reduce the amount of operations. The second one is the use of approximation in adders to reduce area and power. And the last one is to evaluate 3 different kernel sizes to understand the impacts on final results. So, the logical refactoring is composed of 2 ideas. The first one is the exploration of equation redundancies. For example, to obtain the result of the A function, the parcel x plus I plus z appears 2 times. So it's possible to calculate this parcel only once and reuse its result, reducing the number of operations performed. Second idea is the use of multiplier constant multiplication, which ideas is to separate the constant values in power of 2 values, allowing the substitution of multiplications by sums and shifts. For example, the 5 times delta can be separated in 4 plus 1 times delta, and it's in hardware implementation only uses sums and shifts. To approximate the adders, we use the copy strategy, which consists of the substitution of the 1-bit full adders by a direct connection between the adders inputs to the output using buffers. In this specific case of this work, it was possible to remove the carry propagation as it is not used in any bit adders, and it increases area and power savings. In this work, we evaluated 3 different kernel sizes, 3x3, 5x5, and 7x7. To obtain the kernel coefficients, we use the equation G as displayed with the variance equals to 1.36 and the xi values as the coordinates of the kernel matrix positions. To implement the hardware architecture was combining the logical refactoring ideas and the copy strategy. The 3x3 kernel has the smallest number of components and among the evaluated ONs. The 5x5 kernel has a more complex implementation than 3x3, and the last kernel evaluated is the 7x7 that has the most complex implementation and has the largest number of components among the 3 kernels evaluated. So, to evaluate the approximate technique, the 3 architectures were divided into 5 different levels as highlighted in the images. In each level, it's possible to use or not the approximate adders, totalizing 32 different combinations to each kernel. To decide the number of bits approximated in each adder, we evaluated different number of bits approximating using the normalized mean error distance metric. We evaluated the different bit lengths, and the results shows that approximating half of the bits obtains animated results acceptable to be used in the applications. So to evaluate all architectures cases, we developed a C++ framework and used it as input 10 images from the BSD dataset. And to simulate a real-world image capture, we added Gaussian noise to each image. As an application to evaluate all those case filters, we used the KNAD algorithm. The first result is the output of KNAD using each exact kernel size. It's possible to notice that the kernel size impacts the sensibility of KNAD. To 3x3 kernel, the output has more details, while to the larger kernels there are less details in the output image. To evaluate the quality of the outputs, we use the performance metric. This metric is based on the pixel-by-pixel comparison of the output from the exact KNAD and the approximate version of KNAD. The performance is the minimum value between recall and precision functions, where recall is the fraction of all actual positives that are predicted positive, and precision is the fraction of all positive predictions that are the true positives. The performance was also implemented on the C++ framework. The results being displayed were limited to just 7 cases, as all results with level 5 approximate are very close and are below 50%. Small quality results happens due to the shifts are being performed before the adders in level 5, as we can see in the right. To level 1 to 4 approximated, the performance conforming results were between 50 and 9%, showing that approximating those levels did not impact significantly the quality of results. To evaluate the area and power, we selected 18 cases per kernel. Those cases are the 50 best performance-conforming results, and 3 corner cases, the exact one, only with level 5 approximating, and with all levels approximating. To synthesize and simulate was used the synopsis tools with the 45 nanometers TSMC standard cell library, targeting the frequency of 249 MHz, which is enough to process 4K images. Only using the logical refactoring kernel 5x5, the area reduced in 12% and the power in 20%. It is a consequence from the 34% reduction in the total number of 1-bit adders. To the approximate case, the error reduction related to the exact case are shown in the chart. To a single level approximate area reduced up to 8% to all kernels, while to the all levels approximated case reduced up to 41% with a high degradation in performance conformance. Considering level 5 exact, the area reduction was between 6 and 5%. The performance conformance and power reduction trade-off analysis shows that it is better to exploit approximation in multiple levels than in a single level, as the quality results are similar. Approximating only level 5 has a significant impact on quality, with slightly improvement on power efficiency. And the highest power reduction were obtained with all levels approximating, but it has a substantially high impact on quality results. So, as a conclusion, in this paper we discussed 3 approaches to improve and its combination to improve power efficiency of Gaussian filter, which are the logical refactoring, the copy strategy to approximate adders, and 3 different kernel sizes. Based on the results, we can conclude that kernel 3x3 is more suitable for power-constrained applications, while kernel 5x5 has the best trade-off between performance, conformance, and power. Also, kernel 7x7 can be used in a non-power constrained application. As a future work, we aim to develop a configurable kernel to take advantage of kernel size based on the application's constraints. So thank you very much for your attention.